The example reports training on 150 containers across 20 bays and reaching 89% of optimal after 3,500 episodes. It reports handling time reduction from 16.2 hours to 11.8 hours and emergent behaviors like proactive space reservation. Tier 5 introduces an integrated digital twin that continuously updates a simulation of vessel dynamics, port operations, weather, and supply chain impacts. The operational value is resilience. You can adapt the plan when conditions change instead of relying on a static schedule. This figure shows a system of systems architecture for re-stow operations. The key message is that optimization must be coupled to real-time data streams to remain operationally relevant. The digital twin integrates vessel sensors, terminal systems, environmental data, and supply chain network signals. Together, these streams enable dynamic constraint updates and scenario analysis. The digital twin supports weather scenarios, equipment failure simulation, rush cargo integration, and port congestion effects. The output is a set of risk assessments and adjusted plans, not only a single plan. During Typhoon Mangkhut approaching Hong Kong, the example reports a digital twin simulation for vessel MSC Oscar. It recommends delaying re-stow by 4 hours, reducing shifting risk by 67% while increasing port costs by 8%, and postponing 142 of 200 planned moves with 94% prediction accuracy. Tier 7 treats re-stow as collaborative intelligence between humans and artificial intelligence. Humans contribute contextual knowledge and safety intuition, while artificial intelligence contributes optimization, monitoring, and explanation. This figure illustrates the collaboration model and feedback loop. The operational requirement is that recommendations are explainable and adjustable, not a black box. The slide describes 3 modes: artificial intelligence proposed and human refined, human initiated, and artificial intelligence optimized, and collaborative real-time adjustments. These modes reflect how responsibility can shift depending on time pressure and risk. The slide lists explainability methods, including local explanations using Lime and Shapi, global feature importance, counterfactual scenarios, and natural language explanations. Operationally, explainability is what makes supervisors willing to rely on recommendations under time pressure. Trust calibration mechanisms include confidence intervals, historical performance tracking, disagreement highlighting, and gradual autonomy. The goal is to keep trust aligned with measured performance rather than hype. The example describes Supervisor Maria Vanderberg collaborating with the system on vessel OOCL Tokyo, involving 287 containers. The artificial intelligence proposes a 73-move plan. The human adds hazardous constraints, and a revised 81-move plan keeps 95% of the efficiency and avoids a potential 6-hour delay. Tier 9 maps re-stow into quantum-ready optimization forms so that extremely large assignment spaces can be explored more efficiently. The goal is not to replace operational constraints, but to accelerate search for high-quality, feasible assignments. This slide shows the quadratic unconstrained binary optimization form used to encode costs and penalties for assignments. Operationally, the matrix encodes movement costs, stability constraints, discharge requirements, and accessibility limitations. This slide shows a quantum-approximate optimization style state that alternates mixing and problem-specific operators. The key takeaway is conceptual. The algorithm uses structured interference to bias toward low-cost solutions. This figure presents a circuit view for exploring re-stow assignments. The operational takeaway is that measurement yields candidate assignments that can be evaluated and translated into movement plans. This code slide introduces a quantum re-stow optimizer that formulates a quadratic program with binary assignment variables. It defines linear cost terms and quadratic penalties that discourage assigning 2 containers to the same position. This part shows how quadratic penalties are built for position conflicts and how assignment constraints enforce exactly 1 position per container. Operationally, these pieces keep the formulation aligned with physical feasibility. This part shows solving with a quantum approximate optimization method and interpreting the result into an assignment map. The assignment map is the operational output that must then be translated into a movement sequence. This part defines helper functions for movement cost, stability penalty, and sequence penalty. Operationally, these functions encode practical trade-offs like heavy container placement risk and discharge order conflicts. This part continues evaluation logic and shows a condensed example dataset with sample containers and positions. It demonstrates how an optimizer call produces an assignment and a cost. This final code slide completes the condensed pipeline, printing assignment, cost, and optimization time. Operationally, it emphasizes the workflow: formulate, solve, interpret, and evaluate. The example reports testing on an IBM 127-qubit processor called IBM Washington and solving a 45-container re-stow problem in 847 seconds. It reports 94.2% of theoretical optimal cost versus 87.3% for classical simulated annealing, and a 23% reduction in handling time versus classical heuristics. These questions cover building a mixed integer model for 6 containers across 3 bays with a $200 move cost, computing weighted priority scores, demonstrating one ant colony iteration, defining deep reinforcement learning state and masking, and specifying digital twin data fusion and triggers. Treat these as implementation readiness checks. Could you build a working system from the tier definitions? These questions ask you to design a supervisor override interface with explainability and trust mechanisms, and to formulate a 3-container, 3-position case as a quadratic, unconstrained binary optimization matrix and estimate depth for a 2-layer quantum approximate optimization approach. The point is to connect high-level concepts to concrete design decisions. Re-stow is a high-impact problem at transshipment hubs. Tier 1 provides rigor and explicit constraints, and Tier 2 and Tier 3 provide scalable approaches for fast planning. Tier 4 can learn sequential strategies that reduce handling time. Tier 5 adds real-time resilience through simulation. Tier 7 improves decisions through human and artificial intelligence collaboration, and Tier 9 provides a potential acceleration path for very large instances.